All right. So today we're going to see a few examples of using backprop on neural network and how we're going to actually implement one. So you already knew most of the things. We just want to combine them together and present it as a whole package. And next session, we're going to conclude neural networks with some other optimizations for SGD that I talked about like 2 weeks ago. Atom optimizer and also what else? And the other one, Artemis Prop, if I'm not wrong, yeah. Artemis Prop and Atom. And yeah, basically you're good to go with your projects, your assignment. And then next week, I believe, is reading, right? Yeah. Okay. So here's a sample 2-layer neural network. So L is equal to 2, and we want to compute partial E divided by partial Wij. So if you parse the network from left to right, so you're gonna have two inputs, x1 0, x2 0. So they're gonna feed the values here this way as forward prop or forward pass, and then you have W1 1, W1 2 of 1. Also, you're gonna have W2 1, W2 2 for x2 0. So this node, this signal that arrives here called S1 is dependent on W1 1 and W2 1, right? So this value that comes back as the partial value of the changes, which we call it delta. So in order to calculate here, you have to count these two as well. So likewise here, delta 2 1 depends on W1 2 and its input, and also depends on W2 2 and its input. And this is the signal 2 here, signal 2 1. Again, the output of these would be the input of the next layer, and then we do another sigma here. That's why you only have one. That's 1 2, and it would output as x1 2, and this would be the result of your final hypothesis because your candidate. And we're going to check this g function, the value of that, with y, which was the true value, and then you're going to compute the en of your weights, which are omega. Right? So we are interested in computing a sample backprop. So partial E or derivative of E divided by partial Wij. Okay? So as a high level, what we're going to do is, I talked about the chain rule the previous session. So we have to come back as a chain rule as a function of a function of a function for these 2 layers. And when we find a change here that needs to be made because of the loss function, first we have to come back 1 and see if we have this change, what value should be changed here in this node. And then you compute that with the first partial sum of the first rule chain. And then you compute that. So this is like your number 1, and this would be your number 2 delta. And then from here, you're going to see what are the parameters that could have been affecting this, okay? And then you come back 1, you're going to find this here. That would be your third one in the final case, right? So it's a function in a function in a function. That's what was called chain rule, okay? All right, I left the diagram up to have it as a reference. All right, so we start with the first delta. So delta 1 of 2, which is this. The first delta that comes right before the last layer, right? Right before the final classification. So this one can be computed as always as partial E divided by partial x12 because of its own input. Its own input was x12. I'm sorry, it was the output of that. So that was the outer function, and this is the inner function for the chain rule, which was the partial x12 partial s1. So now we carry forward with that. It's obvious that this one is simply the output of the activation, the last activation function, and the value was the value we estimated. It was the least square or yeah, because we did the partial, we went down to theta x12 minus y. And the second one was the theta prime of S12, okay, here. So now we are interested in finding the partial changes of E towards the changes of W11. Because we arrive here, we know that we go after this path and also that path. So the first one would be x1 of 1 delta 1 2. So here. And for the other one, W21, which is here, the other path, we need to is equal to x21 multiply delta 1 2. Okay. So at this point we have to compute these two deltas here. Now we arrive up to the point that we need delta 1 1 and delta 2 1. Okay. So delta 1 1 has another neurons and connections incident there. So it would be equal to partial D divided by partial S11. And this value would be this, which already computed, multiply delta 1 of 2 multiply by x12, because this one already has x1 2 here and delta 1 2 there. For the other case, for delta 2 1, the one behind it, the one below it on the other branch of the network here, so it would be the same, but we have to just change the all right. So now for I1 and 2, because we had two I and J here, the final value should be computed as partial E divided by partial Wij of L, which is equal to Xi of 0. So now we need to compute the very first one. Multiply by Sj1. And I and J are 1 and 2. That's why you have two of them as input and two of them as S's, the signals that coming from the multiplication of X's and W's. Okay. So Let me bring the graph first. Okay. So now we arrive at the point that we need to compute we arrive up to here. So we had one hop here, the second one, and now we're here, and we want to see what was the changes that should be made in this portion of the network so that we can relate to that delta that we received from the previous deltas, right? So here we have two connected S's which are connected to two W's, I1 and 2, which are representing two input x1 and 2. So now delta 1, 0 corresponding to the first one, and delta 2, 0. Let me get rid of this. So for the delta 1, 0, it's going to be the expansion of the chain rule. So W1, 1 of 1, this multiply delta 1 of 1 plus W2, 1, because these two are only connected to this signal, right? Only this and that. Plus W2, 1 of 1 multiplied by delta 2, 1. So the other case would be, so likewise for the delta 2 of 0. Now in this case it would be 2, 1 and 2, 2. All right. So now we finish the backward pass. So given a loss function out of the output, we could backprop all those deltas that needs to be done. So all the nudges we have to be doing on the W's for one iteration. So if you continue going with your SGD or other optimization algorithms, so at each step, this should be repeated, okay? So a simple question would be, what if we force both two W's, W1 and 2, and W2 and 1? I guess this is it. Yeah, this should be 2. Oh no, actually this is right. This is correct. Let's see. So what if we force these two values the same? I mean, suppose they have the same value, right? If you expand the previous one, the partial E divided by partial W in general would be this chain plus the other one. So this we calculated, it was delta 1, 1 here. This relates to the input of that, x2, 0 here. And the other one we computed was delta 2, 1. And partial S2, 1, partial W would be the input of that. So it's going to be simplified this way. So sometimes in your exam when you have multiple W's, we might just put some of them equal or force them equal so you have less of computations to do. But definitely, yeah, study this type of problems because it's probably going to have one in your midterm. All right. So now, let's just recap about the choices of activation functions we could have had in a sample neural network. So starting from logistic regression, we were talking about the sigmoid function that was outputting probability from 0 to 1 for us, right? The output of the activation function. So now let's see what are the other choices. I mean, you might know many of them. We're going to add a couple of more. So let's just recap them all here. So the first one was sigmoid. You already know that. So theta of s was e of s divided by 1 plus e raised to the s. Okay. So that was a signal. It would give you an output from 0 to 1. That was why it was very neat for us in order to compute probabilities, right? Because the output would be somewhere. You could relate that to your likelihood percentage. Then carry on forward, we define the hyperbolic tangent. It had similar behavior, but instead of spanning from 0 to 1 as the output, it would span from -1 to +1. So this would present a more realistic output for our weights. And it would mimic a better soft threshold for our method, right? So for many years, that was the default activation function people were using. So recently, like 4 or 5 years ago, the other activation function called ReLU or rectifier got very common to use. So it's called the rectifier. So as its name resembles, it rectifies the output. So you simply have either 0 as the output when your values are minus, and then when your values are plus, you're going to have them as a linear output. So this yields an interesting property for our neural network. First of all, except some exception actually, or some customized network, most of the recent neural networks and convolutions, CNNs actually were using this. So it has some caveats as well, but it has some advantages. One of the advantages is the computation is pretty easy. You see, we force many weights to 0. Thus, the theta prime of s, which we want to compute at each backprop iteration, is going to be simplified. And on the other case, when the x's are plus, you have the theta prime of s equal to 1 because the slope is linear, right? And it's only 1. So that's why it's default in neural network, and some research has provided insights that they're going to bring up to 6x speed up when you train your model with this activation. It's simple and avoid nonlinearity. However, there are caveats. Can somebody point one caveat here? What would you think can happen when you use a ReLU in the long run or just short run? Any guesses? So, looking at the shape, basically, if you have many minuses as your input, so you're going to have many zeros as output as well, right? And these zeros resembles dead neurons. So when a weight is 0, it's as if you drop one neuron because the W was 0. So suppose you had these nodes and these 3 nodes, okay? And that was the weight connected to the next layer. So if you make this weight 0 on the next layer, it's as if you drop it completely, right? And when you drop this, if there are no other weights outputting from this neuron, this would be dropped as well. So we call this dead neurons. It has itself, it has a complex property, so I'll talk about it a little bit later. So basically one of the caveats of using this is introducing many zeros and dead neurons. Okay? So basically, if your signal is smaller than 0, the output would be 0, thus the theta prime would be 0 again. So you're going to have dead neurons here, okay? And when they are 0, they won't get updated, right? So roughly speaking, in a deep neural network, it might be able to bring around 40% dead neurons. So a recent interesting research in neural networks lies in the name sparsification, or sparsifying neural networks. So this is actually one of my research as well. So when we can exploit this as sparsity, so we call this sparsity as well. So when you have zeros in your model, it's like your network has some degree of sparsity, okay? So you can, later on, if you want to deploy that model, you can use this as sparsity and compute fewer computations, right? If you found that a neuron was dead and the W was 0, so what's the point of computing 0 multiply another 0 plus another 0, right? So you can just compute, you can just drop the whole line and avoid computations. So this path of research is called sparsifying neural networks or convolutional neural networks, and the action would be called sparsification. So although this is a caveat for ReLU, but this also opens up new challenges and opportunities, mostly for mobile devices. Suppose in your mobile devices, you don't want to compute all the steps for a neural network when they are 0. You can just compress the network to a smaller one and avoid computation and save battery, right? All right, so that was the third activation function. Let's go for the other two variation of ReLU. So we call first one leaky ReLU, and the fifth one the parametric ReLU. So both of them are involving with having an alpha here. So instead of forcing all those s's that are smaller than 0 directly to 0, so we're gonna parameterize it using an alpha, and normally the alpha they use is 0.1. So the only difference between these two is leaky ReLU, you force the alpha yourself. On parametric ReLU, this alpha is going to be one of the parameters that should be learned within the training. So as you learn, when you do the forward pass and you get the En of W's, and when you do the backward pass to compute all those deltas, so not only you use the delta to compute the W's, but you can use the deltas to adjust the alpha as well. Because with this ecosystem, you can train whatever parameter you want. You just expand your training and optimization phase, right? So on the parametric ReLU, not only we learn W, but we learn the alpha as well in the process. Any questions so far? All right. So that was one out of three remarks that we wanted to point out for implementation of neural networks. So let's go for the second one. So now that we know several options as a choice for activation function, let's see what options we have for input pre-processing. So what we can do with the input data, can we twist it a little bit to gain more information? Can we just compute more information out of the input data to leverage the training phase? So, and this is in general called input pre-processing. So assume that D was the definition of your input data set. So the vector of x1, y1 up to xn, yn. So that was your data. So one of the things that people are doing, if you also take a look at the ImageNet data set, so there are other auxiliary files that they provide you this information when you want to train a network if you want. I'll talk about it later as well. So when you have this data set, you can compute your mean, which is the arithmetic mean, the vector of mu, pretty straightforward, right? The summation of all divided by the numbers. And also you can compute the variance, the small sigma, for all the j's from 1 to d, so that's the sigma. So it basically the subtraction of each of those x's minus their mu's and square them to find the variance of j for each of those variants, for each of the dimensions, 1 up to d, right? Yeah. And then using this sigma, you can actually normalize your data set. Now you have your input x's for all the i's, and you have the mu's. Let me close it and reopen it. Okay. So now you have the x's. For each of the xi of j, you can compute this minus its average divided by sigma. Okay. So this process is a form of pre-processing your data, and in general, sometimes it is called normalization or standardization. So you pretty much provide a more uniform data as your input of your neural network. So sometimes it is helpful, and it's going to help your model to converge faster. In such a huge data set like ImageNet, when you have more than 1 million training images, so computing this itself takes a long time. So sometimes they provide you with these values as well. Also, the other point about pre-processing is when you have, for instance, on a case of a convolutional neural network, when you are dealing with images, so this could be your input image, right? You have 2 dimensions for x and y's, and also could be a 3rd dimension for the channels of the image. For instance, you have a photo of 299, and that photo was color, right? It wasn't a black and white photo. So it simply had RGB, or depending on the representation of these 3, it could be GBR, so they have different standards. So this yields 3 more dimensions. So at the end you have 299, and 3 as your input. And these are the number of pixels you have, right? So some networks won't accept or just only accept certain amount of inputs, like LeNet 5 Only I accept the smaller 20-something pixels, right? So what you're gonna do with the 299, 299, you have to find the bounding boxes out of those photos, like choosing them here, or choosing, again, different algorithms to choose their, depending on the color scheme and the histogram of the photo. So playing around with the bounding boxes you want to pass through your network yields another pre-processing challenge, right? Sometimes it is called data augmentation as well. So you have to apply a function f of x that transforms your input, and this f could be anything, could be any geometric function like rotation, maybe flipping the images, cropping certain part, scaling. So these are mostly designer's choice and the way you adopt newer problems, you know, with your older neural networks, for instance. Okay? On the case of ImageNet, again, you can download these bounding boxes from the website. If you want to replicate a test, because if you're participating in a competition, the results should be reproducible. So you have to use the same set of data. That's why they provide you with these bounding boxes, maybe. All right, the third and last one that we talk about today is how we're going to initialize the weights. When we start the feed forward process, on the very first iteration, so when k is 1, you don't have anything set, right? You have like 3 inputs fully connected, and then you have 2 more, and then you have 1 output finally, right? So these W's haven't been initialized. You only have the inputs. This could be your images, this could be your signals, this could be your text processing, anything. So how are we going to initialize those W's? And there is a huge problem, and there is a huge portion of research, you know, targeting this interesting problem, because the way you initialize your rate is going to definitely determine the way you're going to convert. So one way would be just to use small random numbers. First of all, what's the issue with initializing all your weights with 0? Are we going to end up with any issues? Like all zeros, all those W's, let's start with 0. What do you think can happen when you do the first backprop? Any guess? So if you initialize all the weights to 0, when you want to compute the theta prime, you can't, because it's going to be equal to 0 again, because it's a multiplication of 0 with your W's, right? So no matter how many times you want to iterate at first, you can't change the weights at all. So you're going to be stuck at the same space, at the same spot you started, right? So initializing the weight to 0 is not going to help you at all to get started. So another point is, what if we initialize them with small random numbers, not 0 but pretty close to 0, like your weights, Wi and j's, at each layer comes from a normal distribution, say from 0 and 10 minus 2, pretty close to 0. So this is one way, because you don't want to initialize very, very big numbers, because the changes would be a lot when you want to do SGD, right? So you want to make sure that you are initializing small enough numbers that can capture the changes of the backprop and with weight adjustment. So it's going to work with the small neural network if you adjust. But in the long run, when you have a deep network, it's going to cause a well-known problem called vanishing gradients. So vanishing gradients is mostly happening in RNNs, recurrent neural networks. So mostly in RNNs. And it's the fact that after certain iterations, say you have started from iteration 0 and then you move on, your weights were like, I'm talking about only 2 weights here, maybe like W2 and W1. Okay? You start them like this. And then after certain iterations, K was maybe 1,000. You see that these values are getting vanished, like they go like this. You carry on, maybe at 10K iteration, you see that they're almost 0 now. Because the changes are going to get lower and lower and lower and fewer, and then it's going to vanish. Your gradients, every time you calculate the loss function, it's going to be like 10 to the raise of minus 25 maybe, right? And after a certain while, you see you won't get, and you're stuck somewhere, and you can go anywhere else. So this is known as vanishing gradients. So initializing small random numbers might yield this problem. All right. So people have put some thought about this problem, and there are 2 other well-known techniques. You can find them also in TensorFlow or Caffe if you use. So the first one is called Javier initialization. So basically, if you got a sigma j as your sigma of your data set for your i's from I to n, you can assign them as n times the variance of w and j, which is actually the definition of that. So Javier initialization generates a sample normal distribution from this 0 and 1 over nth for your w's. It's a very smart trick, because if you generate this, and so this n is actually the number of nodes incidents on node j in layer L. Okay? So you generate your data distribution from this sample. Thus the signals j of L would be equal to the sum of I of from 1 up to n xi L minus 1 divided by multiplied by the wij, and this has a variance of 1 over n. So the interesting part about this initialization method is it's gonna make sure that you want to stock in you want to stock in random spaces in your optimization network, in optimization space, and also it avoids vanishing gradients in most of the cases. Okay, so also it makes sure that the variance of your signal, all of your data, would be a unity matrix. That's why its variance is 1. Okay. combine this Amir initialization with ReLU as well. So the final outcome of the variance would be 2 over n if you compute the final value. Because you use ReLU again, and this has a normal distribution, so it results in mostly half of the neurons being inactive at each layer. So as I mentioned, it has both advantages and caveats of its own. In this case, the biases are going to be initialized typically to small true constants. So as I mentioned, using Amir initialization is going to help you to avoid getting stuck in. So this is stuck in saturated regions. Saturated regions of hyperbolic tangent. Okay. So there could be many other optimization techniques involved, but we just summarize them for the most well-known one that you might need to use for your projects. I'm mostly done for today. So on Friday we're gonna finalize neural network with 2 more optimizations, ADAM and RMS prop, and yeah. We'll conclude with the first half of the semester. Any questions? All right. Have a good day, guys. See you on Friday.